This is video lecture number 7. So thus far in class, we've talked about internal validity and external validity and minimizing, to the extent we can, threats to our validity. And the way to do that is through good and careful research design. Now, research design could actually make up an entire semester's course, but we're going to, in this class, just consider a few different generic kinds of research design. I've broken it down here into 3 categories. One category that I would actually consider pre-experimental, and what I mean by that is that perhaps the observations one can make in a pre-experimental kind of study would be a great launching pad for later research, but with a pre-experimental design, you can't really validly make a cause and effect connection. And the next couple of categories, true experiments and quasi-experiments, can actually be very sophisticated and can allow those kinds of cause and effect analyses at the end. The first type of pre-experimental design, so to speak, we're going to talk about is the case study. Case studies, of course, are just a description and analysis of one particular subject. Maybe a good place to start, a good place to formulate a hypothesis, but a case study all by itself is not really science. For example, let's say someone who has a cold is given large doses of vitamin C, and then lo and behold, a few days later, the cold is gone. We can all understand why a case study like this shouldn't be relied upon as evidence that vitamin C cures colds. This is really no different than someone with a cold being bled with leeches and then getting better. Neither one of the examples really tells you what effect, if any, the vitamin C or leeches had. The colds could have been cured by bed rest or cured by drinking fluids. Those would be possible history confounds, or more likely just the cold was cured by the person's immune system, which would be a maturity confound. Despite the weaknesses in the case study approach, it's very common to see it used in advertising. These case study ads can be very convincing. Advertising agents know that people respond better to individual stories than to some generalized information about a product or drug. A few examples on the slide here. We have the Bowflex guy who spent 20 minutes a day with his Bowflex and got this body. Here on the top in the middle, we have a hypothetical child, probably hypothetical child, used in an ad for some drug that teaches attention deficit hyperactive disorder. Very common in these ads to see a particular child's case described. And the use of many of these drugs has become a very controversial topic, with many scientists and doctors saying that we're over-medicating not just children in the case of the ADHD drugs, but all of us with regard to a lot of the prescription pharmaceuticals that are advertised. But certainly these ads have increased demand for a lot of these drugs. On the top right here, we have one of the most famous case studies of all time, Freud's Anna O. Anna O was diagnosed with so-called hysteria that was apparently cured by Freud's talking therapy. That was the genesis of Freudian analysis. Down here on the bottom of the slide from right to left, we have Bob of Enzyte male enhancement fame. Kathy here, the depressed white blob who's cured by Zoloft, an antidepressant in the selective serotonin reuptake inhibitor class. Another really interesting example, controversial to some. Many randomized controlled trials show that antidepressants in most people don't work better than a placebo. And finally, over here, we see former NFL quarterback Steve Young extolling the virtues of Advil. So, despite concerns we might have about case studies in advertising, case studies can be very good at generating hypotheses, getting a feel for a subject area, and certainly sometimes cases are chosen for publication because they're unusual or particularly interesting. As a scientist, you might get an idea to study something because you observe something unusual, but you do run into problems if you try to just use case studies to validate your hypothesis. So the value in any case study or even a series of case studies depends completely on the researcher. No way for a third person to know the validity or replicate that work. And of course, there are no control groups or comparison groups, so you can never tell what the results would have been had the author or the researcher chosen a different case. It's kind of like the difference between your cousin telling you, oh, yeah, my friend Phil owned a Honda Civic and he loved it. He never had a breakdown in 8 years, versus looking at Consumer Reports to see the overall safety and reliability data on the Honda Civic. And one frustrating thing for reputable scientists is that case studies can often be incredibly vivid and can have an enormous effect on the reader or listener or on a consumer. And that can lead to misinformation being spread and actual scientific data that may not be as sexy getting ignored altogether. Our next illustrative example of a pre-experiment is the one group pre-test, post-test design. This is very weak design, subject to many, many confounds. So in this type of design, you only have one group of subjects, and they're pre-tested on the dependent variable and then post-tested after the treatment or intervention has been administered, after the independent variable has been administered. So using the vitamin C example again, if you take 100 people that you've chosen specifically because they have colds, that's your pre-test phase, then you give them all high doses of vitamin C and then test them a week later, and that's the post-test phase. Well, you might find that 50 of them don't have colds anymore, but the exact same confounds are there that were there in our one-person vitamin C case study. But here, even more possible confounds applicable in a multiple subject study, like mortality, for example. You can't assume that people are dropping out for a random reason. Still, though, the major problem is that the study just doesn't give you much support at all for causation. Not having a comparison group, for example, is the big flaw. And if you're interested in this South Park meme, you should just look up South Park ski instructor. The last kind of pre-experimental design I want to mention is the static group design. This is really just a weak observational or correlational study. In a static group study, you do take two groups. You have two groups denoted here in the diagram by the 0 timeline, or the two groups are the groups up here at the top and the groups down here at the top. 0 is the timeline that you're beginning your study. But you take two groups, and one group, the members of the group has been exposed to a certain thing or subjected to a certain treatment in the past, which is denoted here by the X, which takes place before you even start measuring anything in these groups. And then you see how your two groups perform on a certain measure. So in a pre-experimental type static group design, there's no control by a researcher about who ends up in the two groups. Most of the time, it's just going to be people who have self-selected at some point in the past. For example, you might want to look at people who have smoked 2 packs a day of cigarettes for the past 10 years and compare them to people who've never smoked. And the researcher just takes the groups as she finds them, categorizes them based solely on her design, without regard to whether the people in the groups are also different from each other in other characteristics. So again, in our vitamin C example, a researcher might recruit people who say they've been taking at or above a certain dose of vitamin C for at least some minimum period of time. And then you have a control group of sorts with people who have not been taking vitamin C, and then follow them for 6 months to see how many colds people in the two groups get. So there you would have no random assignments to groups and not even a purposeful assignment to groups. You're just measuring some variable of interest at a certain point in time or over a period of time, but clearly subject to a lot of internal validity threats. The history threat might be there in that you have no way of knowing how your two groups might differ, aside from the one independent variable of claimed vitamin C use. People, for example, who take vitamin C might do other things to keep healthy, like getting 8 hours of sleep a night or exercising. For that matter, taking other kinds of vitamins or supplements. That's going to be a history confound. And somewhat related to that might be the selection confound of being healthier to start with, or if their immune systems are stronger due to factors other than the vitamin C regimen, there might be a maturation confound in that they fight off any viruses they are exposed to in a more efficient and quick way. On the slide, I have a couple of quotes from one of the classic research methods books, Campbell and Stanley from 1963, which I think really well describe the problem with this simplistic research design. So you might want to just stop the video here and read those quotes. They might help clarify here. But this kind of simplistic static group design study, essentially just an observational study, can't strongly support a cause and effect claim. Now, it also is a correlational study, right, in that you're looking at groups along one measure and seeing if the differences in that measure are correlated with another difference, like whether the group taking vitamin C has an overall lower number of colds. So in the next video, we're going to talk about some more sophisticated correlational studies, which can be considered to be more quasi-experimental. So we're going to go into what quasi-experimental means.